First of all, let me thank the organizers for giving me the chance to give this talk and all the people who decided to stay in this room. I'm going to talk about this work done in collaboration with Daniel Lidar, which is about applying optimal stopping ideas to revisit the benchmarking of randomized optimization algorithm. Now, do we need to revise this process? I don't have to convince you about the importance of doing benchmarking. We rely on it to pick our best solver, and we also rely on it to try to detect quantum speedup, for example. But today you have heard already about at least a couple of ways of addressing the performance of a optimization algorithm. Usually what people do, and we can be happy about that, is compute time to solution. But Helmut Katzgraf was talking about doing fair sampling. So already you heard this first day about different ways of doing benchmarking. And maybe tomorrow you'll learn about doing time to target measures. So my first important point is that there is not a unique way of doing benchmarking, but whenever you choose your strategy, this should be always been very clearly motivated by a practical or a theoretical reason. And what is our practical motivation or practical situation? Yeah, we put ourselves in a situation where all solutions that we get from a solver are acceptable. And of course, we want better solutions, but we have to also deal with our computational length. And we deal with a situation where the computation length is not fixed, OK? So I think we understand we somehow, there's a way to go beyond time to solution and time to target measures. And this is because there is this intuitive trade-off between time and energy. Of course, the more the computation lasts, the higher are the chances that I'm going to find a better solution, a better approximation of the ground state. So if we have this energy-time trade-off, can we find an optimal balance? And to try to formalize this question, I would like to define a total cost, which is a function of time, and this is the sum of best energy, which is the best energy found at time t. And t, of course, is my computational length. And then a function, a cost function that measures the computational effort. And think of this as what you have to pay for keep your computation going. Your energy bill, so you can put into this function the price you have to pay for your hardware, these kind of things. And now the question is, can we minimize this total cost by choosing a time to stop the computation? Now this looks like a hard problem, and indeed it's a very hard problem in general, but we can actually make progress if we have make an assumption. And the assumption is that simply we deal with randomized optimization algorithms. And for us, a randomized optimization algorithm is simply a black box. Well, that's not really a black box. That's more like a black box, okay, that draws random samples from an intrinsic distribution. Okay? And this intrinsic distribution will depend on the problem instance, on the parameters that are used to set up the solver. But that's the main assumption. The solver is basically a sampler of random energies, okay? Of a sampler of energies. And assume that once I have fixed my instance and my parameters, the solver, I can run it many times, and the computation will last T1, which is basically fixed. Now, most solvers are easily modeled by this assumption. Classical heuristics like simulated annealing, quantum Monte Carlo, genetic algorithms include parallel temperings, and basically all the algorithms that you have seen so far, they can be modeled by this. And also quantum optimizers, whether they are adiabatic or quantum annealers, or whether it's an algorithm defined on the gate model, because it's a quantum algorithm, because you have some randomness in the measurement process, you can think of any quantum optimizers as a randomized optimization algorithm. So it's a very general assumption. If you do this, we see that our total cost becomes discretized in steps of T1. And now I would like to define my total cost like this, sum of the best energy that I found at step n I assume here I draw n samples. I run my solvers n times. And then a little slightly smaller additional assumption, my total cost now is a function linear in time. Okay? If I do that, I can actually make even further progress. But you see here, I have now sequential decision problem that I have. I can either stop at step n and accept En as my best energy, or pay a price CT run and draw in another sample. And minimizing this cost function is equivalent to find an optimal stopping rule that tells me where I should stop my computation. Actually, the field of sequential statistical analysis provides a theoretical framework to tackle this optimal stopping problem. And actually, what I have defined here is a problem that is known as the house-selling problem. And actually, I can solve this problem well, this problem has been solved analytically. And the solution is made of two steps. The first step is the principle of optimality. And it tells me that if I know the optimal cost, which is the minimized total cost, then I have to stop as soon as I find an energy that is smaller or equal than, as soon as I find an energy that is as large as the optimal cost. This is simple. And the hard part is to compute this optimal cost. And this is the second part of the solution. I have to solve the optimality equation, which is an integral equation for this optimal cost. And this tells me that the optimal cost depends on the probability distribution, that is a property of my solver, of course also my instance, and the cost per unit of time c. So it's a function of c2, which is now for me as a parameter. Now, an important point for me and for us is that the contribution of the tail of p, of the lower tail of p, is negligible if the values of c star is large enough. So I can actually compute c star even if I don't know the ground state. So I can apply this even to do benchmarking even when the ground state is not known. And actually, the optimal cost is basically an energy target. This is because the sequence of observations is stopped as soon as I found an energy that is small enough. And in this case, I can split the optimal cost as an optimal energy, which tells me what is the optimal quality of the function that I'm getting, plus an optimal computational effort, which is basically proportional to the time to obtain an energy that is below this target. Okay, so this optimal cost is really an energy target. But by defining my target as an optimal cost, I achieve the optimal balance between the quality of my energy, the quality of the solutions that I can get, and the computational effort given by this function. And I would like to stress again that our optimal cost plays the crucial role in our benchmarking process. Two solvers can perform equally well if they achieve the same optimal cost, but they may do so with a different balance between energy and time. And I just want to say that the optimal cost actually include other common measures. For example, when the cost of my computation given by my parameter c goes to 0, it's optimal to stop when I found the ground state. So the optimal cost is basically equivalent to time to solution. This optimal cost is proportional to the time to find the ground state. So this limit reduces to a time to solution. In the opposite limit, my cost, the effort, my computation is so expensive that it's optimal to stop after just drawing one sample. So you see in this opposite limit, a total cost reduced to a quantity that may be of interest, which is the average energy obtained by the solver. It's just the same thing. So actually, with an appropriate choice of my cost function Tn, the optimal cost can be reduced to other more or commonly used benchmarking measures. And what I want to say is that from this point of view, optimal stopping and optimal cost provide a flexible and general framework for benchmarking randomized optimization algorithms. In the second part of my talk, I would like to illustrate these ideas by doing some numerical experiment. So we have generated range 3 instances with planted solutions. If you don't know what these instances are, doesn't matter. You can read this paper, but it's not important for this talk. But we have generated 100 instances per side on the chimera connectivity of the D-Way2X device that it's installed at USC. And we have done that for several sizes. This is the size of the chimera connectivity. And we have considered a bunch of solvers, simulated annealing, HFS, and D-Way2X, okay? So let's start with the simulated annealing. And so let's pick one instance on the largest size. We run simulated annealing 10 to the 5 times. And we build our, and we do this as a benchmarking exercise to learn the energy distribution that is a characteristic of my simulated annealing solver. And if I do this for 2 different values of the number of spin updates, the blue line is for 10 to the 5 spin updates. The red one is for 5 times 10 to the 5 spin updates. You see, of course, that if I increase the number of spin updates, the energy distribution is pushed towards smaller, better values of the energies. This is intuitive, of course. But what is optimal? What is the optimal choice for this solver? Now, in terms of optimal cost, the answer is shown on the figure on the right. This is the optimal cost for the corresponding energy histograms. And so you see that the answer depends on the value of the constant C, which in this graph is a cost per microsecond, okay? And so you see that when C is small, it's optimal to do more updates, while when C is large, the computation is expensive, so expensive that it's optimal to run simulated annealing with a fewer number of updates. So the answer, actually, of how should I optimize a simulated annealing depends on the value of my constant C, okay? Even on the same instance and using the same solver. And we can see the effect of these optimization problems if I plot the optimal cost in blue, the optimal energy in red, and the optimal computational effort in yellow. The bold lines are when SA is optimized. The number of spin updates is optimized. And the dashed line is with simulated annealing run at a fixed number of spin updates. And so you see that when C is small, it's by running simulated annealing with a larger number of spin updates, I can get better solutions than what I can if I fix the number of spin updates. But on the other hand, if my cost is very large, the effect of optimizing the optimal cost is to avoid a blow up of the computational effort. I have to keep the computation under control, but I pay the price of getting solutions with a higher energy or worse quality. So this energy time trade-off, it's even more obviously shown in these figures. It's the same instance, simulated annealing. The number of spin updates is optimized as a function of C. And here you see C is, the value C is codified in the color of the dots here. On the y-axis, I have the time to stop, the optimal time to stop my computation. And on the x-axis, I have the optimal energy of the solutions that I get. So you see that when C grows, let's say when C is very, very small, it's like the red dot. It's optimal to find the ground state, so I'm here at 0. And on the y-axis, here I basically have a time to solution. When C is large, I have to give up in finding the ground state. But I have the advantage of reducing the computational time. So, and this energy and time trade-off is what I need to do to optimize my total cost. Okay. So now I would like to compare optimal cost on different solvers, and I have averaged the optimal cost over 100 instances for the largest size. In blue, it's simulated annealing. In red is HFS. in yellow is dy to x. And the comparison here, there is a wall clock time. This is a wall clock time comparison. So this is done by using these numbers here, which is a typical timing for standard CPUs on a single core. So you see that, again, the choice, for example, of your best solver depends, again, on C. So for example, you see that when C is small, HFS is slightly better than simulated annealing. So for longer computation, on when the cost to compute is small, I would prefer HFS. But then for large C, actually, I should prefer simulated annealing. And D-Wave sits here, which seems to be better on this wall clock time comparison for most of values of C. But D-Wave to X is not optimized. The annealing time of D-Wave is not optimized. Well, it's optimized in the sense that it's always optimal to run D-Wave at its shortest annealing time, 5 microseconds. But for example, you see that at the very end, simulated annealing is better than D-Wave just because computing is so expensive that I should try to make this computational length shorter, but that's the minimum value. So again, the main point here is that in terms of optimal cost, the choice of the solver depends on what's my guess for the constant C, which defines how much effort and how expensive it is to do my computation. And the last slide is a scaling study, just to illustrate how scaling works with optimal cost. So now I have here simulated annealing. I have the averaged optimal cost for 100 instances for the sites. And it is actually, I didn't say it before, but this is actually the optimal cost minus the ground state, just to show, just to have a better, just to be able to plot this on a log. But this is just a constant. So you see that when the size increase, the difference between the optimal cost and the ground state increases. And this is intuitive. It tells me that the problems are getting harder, and then it's optimal to stop at a larger, distances from the ground state. And so I can see how this optimal cost scale with the problem size, which is what I'm plotting here on the right, for the 3 solvers, the 3 colors, and for 2 different values of the constant C. These 3 lines are for a small value of the cost C, and these 3 for a large value of the cost C. So you see that for very small C, as I said before, that the optimal cost is basically equivalent to computing time to solution. And so you see here an exponential scaling, as you expect. Now, look at large C. Here, I'm not looking for the ground state because it's too expensive for me to hope to find the ground state. But the optimal cost is minimized, and actually the scaling here is these fits are a linear fit. So you see actually that experimentally see this kind of scaling, and actually the separation between the exponential scaling and the linear scaling is given by the value of C, where C is equal to the first excited state. So as soon as the optimal cost is smaller than the first excited state, I basically looking for the ground state, and this scales exponentially. When the optimal cost is equal to the ground state, to the first excited state, I'm starting to give up to look for the ground state. I have to optimize my cost differently by accepting worse solutions. And from this point going on, the scaling is linear. Okay? And this is what I want to say. I have time, 2 minutes, for the 20 or for the 15? OK. Yeah, so let me just say something that may be interesting. 2 minutes for the 18th. OK. So I will conclude. So we propose an approach to benchmarking that is based on optimal cost. And we put this into an optimal stopping framework. And we show that optimal stopping provides a flexible and rigorous framework for benchmarking. We have shown how to use optimal cost in practice to optimize and compare different optimization algorithms. And on a more technical side, we have seen that optimal costs have this exponential plus polynomial scaling. And although the scaling that I showed before are special of the kind of instances that the square root here and the linear scaling here is special of this type of instances, but an exponential plus polynomial scaling is what you expect in general. So yeah, that's all.
Are there questions for Walter? Kathy?
The last chart you showed, are those still the range 3 problems?
Excuse me?
They're the range 3 random problems?
Yes, these are, so we have here 100 instances per problem site, range 3 instances generated on the Chimera graph, yes. And yeah.
And if I understood you correctly, the bottom curves on the right are finding ground states? On the right, I'm sorry.
So you see here there is a small C region where C has a linear dependence on C. This is the regime where I'm finding the ground state, okay? It's optimal to find the ground state. And it's basically when C is below the first excited state, which in my unit is like about 1 or 2, is a few units, okay? So this is minus the ground state. The first excited state will be around here. So you see that below this, C grows linearly. That means that it basically is telling me that I'm finding the ground state. So this time to solution times the constant C. That's why there is a linear increase. But then there is after this linear dependence, there is a sublinear regime, which is when I am actually giving up to find the ground state. Okay? Here it's optimal to stop before I found the ground state. So I give up, and I have to give up to keep the computational effort under control. Otherwise, you can imagine this, because of this exponential scaling, the computational effort grows exponentially.
So
but
on the right-hand side,
yeah.
The bottom curve is finding optimals.
Yeah, so these 3 lines, okay, this is only SA.
Okay. All right, thank you.
So with some of these constraint satisfaction problem, there is hardness results not just on the problem, but on the approximation ratio. Does your work factor in some of those ideas, or are they aligned in some way?
No, so of course this, I think the fact that eventually you get a polynomial scaling is related to this, to the fact that you may have polynomial time approximation algorithm. But this approach doesn't use those ideas at all. And actually, this is, from a different perspective, it tells you more in a way. It tells you which, so for example, sometimes people have this time to target measure where you fix the quality of your solution to be a few % of the ground state, okay? Now that you can think of it as being an arbitrary decision. Why should be 1% or 2%, okay? So what you do with this optimal cost is that this optimality equation tells you exactly what's that percentage you have to aim for. Okay, so by balancing your target energy and your computational cost, you know what's your target energy and when you have to stop. So it actually tells you these 2 things,
Well, thank Walter again.
Thank you.